We're going to be returning to our example with the squirrel's velocity going from point A to point B, or pole A to pole B. We did this example when we talked about particle and linear motion. Let's read this again. The velocity of the squirrel in feet per second scattering across a straight electric line starting from pole A and traveling to pole B is given by the graph below. Now I do want to mention the fact that its velocity's units is not meters per second. In this case, it's feet per second. So if we go down, this is what the squirrel's velocity looks like, and I've put it in orange because I'm about to do something and show you the difference between velocity and speed. As a reminder, for example, at 0 it has a 0 velocity. At time t equals 2, it's going -2 feet per second. At time t equals 3, back to 0 feet per second. At time t equals 4, it's going 2 feet per second. So perhaps it would be helpful to put the units up here at the top, right? Now ultimately, here's what the question is going to ask. Find the average speed of the squirrel from t equals 2 to t equals 6. Okay, so here's my a value, and here is my b value. However, what's the question asking? The question is asking for the average speed. So how does speed and velocity differ? Well, this kind of goes back to the previous example we just did. If this is the velocity function graphed, all you have to do is take any part of the velocity that's below the t-axis and put it above the t-axis to make it speed. So for example, this first part is going to look like this, second part like this. Now from here to here, all this is above the t-axis, so I don't have to flip it because it's all positive. But once we get right here again at 11, we have to flip it and put it above the t-axis. So this pink line right here is my speed function. Again, that's because speed has to always be positive. And again, speed is just the absolute value of velocity, or just taking anything that's below the t-axis for velocity and flipping it and making it positive. So this pink graph right here is the speed of our squirrel. Very simple, right? Very, very simple. So for example, at t equals 2, while the velocity is -2, the speed is +2. You're making it positive. So we want to find the average speed, or the average y value of this pink graph right here. And so right now I can just look and see it's going to be somewhere in between 0 and 2, right? The average of all these y values. Okay, the question is, what exactly is that? Okay, well, fortunately we have a formula, right? It's 1 over b minus a of the integral. And the integral we can figure out by finding this area. So for the area, I'm going to use a different color. We'll do purple. This purple will represent the integral. And if we multiply that by 1 over b minus a, we will get the average speed. Okay, so our a value is going to be 0. Our b value, let's get the right color here. Actually, what did the question say? It said from t equals 2 to t equals 6. I'm sorry. So our a value is going to be at t equals 2. So right here. Okay, so this is our a value. Our b value is going to be right here. So all we have to do is figure out the area, this area and basically this area, and then multiply it by 1 over 6 minus 2, and that will give us the average speed. Okay, so actually if I go back and shade this correctly, this is the shaded region we're concerned with, and then we're going to multiply it by 1 over 6 minus 2, or 1 over 4, and that will give us the average speed of the squirrel. So let's go ahead and label the interval a to b. A is equal to 2, b is equal to 6. Write out the formula. The average value is 1 over b minus a times the integral from a to b of f of x. Plug in f of x, a, and b for step 3. So the average speed is 1 over 6 minus 2 times the absolute value of v of t from 2 to 6. Which again, I've already shown graphically is just this pink graph because we're just flipping the velocity. So we're finding this area basically right here, which is a triangle, this area right here, which first part is a triangle, the second part comes from subtracting a rectangle and a semicircle. Again, we've already done this example with particle motion. Okay, so let's keep going. All right, now we're going to determine the definite integral. To determine the definite integral, find the net area under the curve from t equals 2 to t equals 6. Actually, this word is wrong here. Okay, why? Because we're talking about speed, right? So it's not net area that we need to figure out. It is sine. Be total area. Okay, so basically all the area needs to be positive because it's speed from t equals 2 to t equals 6. So again, area 1 right here is just a triangle. The second area from 3 to 4 is a triangle. The third area is a square minus a quarter of a circle. So basically, if you take this square right here and subtract this fourth piece of this total circle right here, you will get this last little purple area right here from 4 to 5. Again, we've done this example in particle motion, so I encourage you to go back and watch that. The area of the first triangle is just going to be half base times height, so 1/2 of 1 times 2, which is just 1. I'm going to try to color code this stuff so you don't get confused. So the area of this first little triangle is 1. Now everybody can probably see that the second area is going to be exactly the same, right? It's just basically the same thing flipped over. So that doesn't really require, oh, that's actually what I already did. So area 1 and area 2 are both equal to 1. The third area, the semicircle, I'll go ahead and make, we'll just make it brown. And if you take the area of this square and subtract the area of this quarter circle, you get this brown area right here. The side length of the square is 2, and then the area of the semicircle is the area of the quarter circle is 1/4 pi r squared, or quarter of the circle. The radius of that circle is 2, so we ended up with 4 minus pi as the area of that third little region. Add all them up, it's area 1 plus area 2 plus area 3, 1 plus 4 minus pi. We get 6 minus pi. Okay, so the average speed is just, so basically this integral right here we just figured out using geometry is 6 minus pi. And we're going to multiply that by 1 over b minus a, or 1 over 4. So we get 1 over 4 times 6 minus pi is going to give us our average speed. And I'm going to answer verbally. The average speed of the squirrel from t equals 2 to t equals 6 is 1/4 6 minus pi. Now, if you find that as a decimal, that's around 0.715 if you plug this into your calculator. So for conceptual purposes, the squirrel is traveling at an average rate of 0.715 feet per second from time t equals 2 to t equals 6. Now, that is an average speed, okay? That is an average speed. So it's going less than 1 foot per second from t equals 2 to t equals 6 on this interval. And that's it for this example. That's all you have to do. The crux of this, the main gist of this, is if you're given the velocity graph, you need to flip it, make it positive, and then find the relative or the relevant areas on your particular interval. So from 2 to 6, we want to find these areas, add them up, and then multiply by 1 over b minus a, in this particular example, 1 over 6 minus 2, and that will give us the average speed of the squirrel from 2 to 6. Conceptually, you can see, and I'll try to mimic this with, so let's just suppose down here is the actual squirrel traveling. So at time t equals 2, it's going 2 feet per second, which is indicated right here, but by the time it gets to 3, it basically stops, right? It becomes 0. Then from 3 to 4, it starts to speed back. It speeds back up to 2. Then from 4 to 6, it slows back down until its speed is 0. So what this question really means is, what was its average speed between 0 and 6? And the answer we got was 1 over 4 times 6 minus pi, or an average of 0.715 feet per second on this interval. If you have any other questions about this example, let me know.